We observe it every day. Millions of people routinely act against pure economic self-interest to give away their own money. This behavior scales up to massive collective action events, where millions of dollars are raised through individual donations. To study this behavior in the lab, economists use the voluntary contribution mechanism, or VCM. In this game, subjects get a set of tokens. Every token kept in a private account pays the individual exactly 1 cent, but a token put into a group account pays half a cent, or a marginal per capita return of 0.5, to every single person in the group. This creates a strict tension. The dominant strategy for a perfectly self-interested player is to contribute exactly 0, while letting everyone else fund the group account. Yet the Pareto-efficient outcome, the scenario where the group makes the absolute maximum amount of money, requires every player to contribute their entire endowment. When this game is actually played, the results baffle theorists. Subjects routinely start by giving 40 to 60% of their endowment to the group. Over 10 rounds, those contributions slowly decay, but they almost never drop to 0. Faced with these numbers, behavioral economists traditionally concluded that this behavior was driven by social motives. They labeled it pure altruism, reciprocity, or the psychological warm glow of giving. There is a strict mathematical trap hidden inside the standard VCM design. The theoretical equilibrium prediction rests exactly on a lower boundary, 0. Because a subject cannot contribute less than 0 tokens, any cognitive error, random click, or basic misunderstanding of the rules can only push the data in one direction, upwards. Statistical errors cannot average out around this equilibrium. On a spreadsheet, a perfectly confused subject looks exactly identical to a highly cooperative, altruistic subject. If we only have access to observable financial choices, how can we mathematically separate an intentional act of kindness from an accidental error? To measure an unobservable psychological motive, experimental economists must design a mechanism that systematically neutralizes it. In 1995, economist James Andreoni at the University of Wisconsin-Madison engineered the first systematic attempt to separate these two variables. He started with a baseline regular condition, which perfectly replicated the standard VCM game where subjects were paid their exact experimental earnings. Then he introduced his treatment, the rank condition. Here, subjects were paid based exclusively on how their experimental earnings ranked against the other 4 group members. First place received exactly 95 cents, while last place received 65 cents. This ranking mechanism mathematically transforms the positive-sum public goods game into a strict zero-sum environment. Putting a token in the group pot now directly lowers the contributor's rank, while mathematically boosting the rank of their rivals. The dominant economic strategy remains exactly the same: contribute 0. But the zero-sum structure successfully eradicates any financial or reciprocal incentive to be generous. Because all social motives have been mathematically neutralized, any positive contribution a subject makes in the rank condition must, by definition, be pure confusion. Comparing the regular condition directly to the rank condition introduces a confound. Subjects in the rank condition receive extra information, their exact standing in the group, which might alter their focus. Andreoni solved this by creating a reg-rank control condition. These subjects were paid normally, based on their earnings, but were also shown the rank information, isolating the psychological effect of the information itself. This setup creates a precise mathematical deduction. If the rank condition equals the lower bound of confusion, then subtracting rank from reg rank isolates the lower bound of kindness. Applying this equation to the data reveals a stark reality. In the very first round of the game, 81% of all cooperation is actually just confusion. Tracking the data over the middle rounds, the confusion block shrinks rapidly as subjects figure out the rules. Meanwhile, the kindness block grows, accounting for about 60% of cooperation by round 5, before finally sputtering out. Andreoni concluded that the cooperative decay we observe over 10 rounds is not driven by learning. Instead, it is the result of frustrated attempts at kindness. Subjects want to cooperate, but they abandon the effort when they watch others freeride. A few years later, researchers Daniel Hauser and Robert Kurzband at the University of Arizona revisited this exact puzzle. They identified a potential flaw. Andreoni's rank condition introduces a complex zero-sum layer of mental math. This added difficulty might artificially inflate subject confusion in the exact condition designed to measure it. Furthermore, because the rank condition is strictly zero-sum, a subject trying to be purely altruistic, intentionally taking the lowest payout to ensure others get the highest, would be incorrectly logged as confused. Hauser and Kurzban set out to build a cleaner trap. They needed a design that removed social motives without adding complex layers of payoff math. This highlights a central paradox in experimental economics. The mechanism you build to measure an unobservable variable must not be so cognitively heavy that it alters the variable itself. Their solution was the computer condition. Instead of changing the payoff math, they kept the standard VCM rules entirely intact, but replaced the human group members with pre-programmed robots. The identification logic here is tight. A human cannot genuinely benefit a computer or trigger robotic reciprocity. With social motives voided, any contribution in this condition is strictly confusion. To prevent subjects from trying to game the algorithm, they instituted a strict procedural control. The human player is told exactly how many tokens the computers will contribute before making their own choice. This chart shows Hauser and Kurzban's results, tracking mean contribution over 10 rounds for the human condition on top and the computer condition on the bottom. The gap between these two lines represents intentional kindness. Notice that the width of this gap remains surprisingly stable across all 10 rounds. Now look at the slope of the bottom line. Confusion starts high, but it decays sharply as the rounds progress. Hauser and Kurzban reached a contradictory finding. Cooperative decay in public goods games is not caused by frustrated kindness. It happens simply because subjects learn the rules and make fewer mistakes over time. Placing these two methodologies side by side allows us to evaluate their structural biases. Andreoni's complex rank design was structurally biased toward finding confusion. His results represent the absolute ceiling of the phenomenon. In contrast, Hauser and Kurzban's transparent computer design was structurally biased against finding confusion, representing the absolute floor. Despite using diametrically opposed methods with opposite biases, both papers proved the exact same thing. At least 50% of anomalous cooperation in these games is merely confusion. This provides a critical lesson for reading and designing any economic experiment. Boundary equilibrium models are inherently dangerous. When structural constraints force random variance to flow in only one measurable direction, the data will always skew upward. Researchers cannot simply look at a chart showing above equilibrium behavior and assume the subjects are driven by altruism, fairness, or a warm glow. Before the field invents complex psychological theories to explain irrational market behavior, economists must first design rigorous mechanisms to prove the subjects aren't simply misunderstanding the rules.